Good morning. I am Mrs.S.ARULJOTHI, Assistant Professor of Physics, A.D.M.COLEGE for Women, NAGAPATTINam. Today's session we are going to learn superconductor. Superconductivity, types of superconductivity, superconductivity material, properties of superconductivity, then application of superconductivity. What is superconductivity? Superconductivity is defined as the substance that offers no resistance to the electric current when it became colder than a critical temperature. Superconductivity is the ability of certain materials to conduct electric current with practically zero resistance. This capacity produces interesting and potentially useful effect for a material to behave as a superconductor. Low temperature are required. Some of the popular examples of superconductor are aluminum, magnesium dichloride, niobium, copper oxide, yttrium, barium. Superconductor examples. Superconductors have been employed in or proposed for use in an enormous variety of applications. Examples include high-speed magnetic levitation train, magnetic resonance imaging equipment, ultra-high-speed computer chips, high-capacity digital memory chips, alternative energy storage system, radio frequency filters, a radio frequency amplifier, sensitive visible light and infrared detector, miniaturized wireless transmitting antenna system to detect submarines and underwater mines, and gyroscope for Earth orbiting satellite. The Josephson junction and the superconducting quantum interference device use superconductor. This is the superconductor graph. Normal metal, superconductor, electric intensity, and then temperature. Types of superconductor. Superconductor are classified into two, namely type 1 superconductor, then type 2 superconductor. First of all, type 1 superconductor is the Mrs.S.ARULJOTHI effect. Then type 2 superconductor is mixed state. Type 1 superconductor. This kind of superconductor includes the basic conductive parts, and these are utilized in different fields from electric cabling to microchips on the computer. These types of superconductor lose their superconductivity very simply when it placed in the magnetic field and the critical magnetic field. After that, it will become like a conductor. These types of semiconductor are also named as soft superconductor due to the reason of loss of superconductivity. These superconductor obey the Mrs.S.ARULJOTHI effect completely. The superconductor examples of zinc and aluminium. This type of superconductivity is normally exhibited by pure metals, example aluminium, lead and mercury. Then type 2 superconductor. This kind of superconductor will lose their superconductivity slowly but not simply, as it's arranged within the exterior magnetic field. When the second type semiconductor is placed within a magnetic field, then it will lose its superconductivity slowly. This kind of superconductor will start to lose their superconductivity on the less significant magnetic field and totally drop their superconductivity at higher critical magnetic field. The condition between the slightly critical magnetic field and the higher critical magnetic field is called intermediate state, otherwise vortex states. This type of semiconductor is also named hard superconductor due to the reason they lost their superconductivity slowly but not simply. This semiconductor will obey the effect of Mrs.S.ARULJOTHI effect but not totally. The best example of this niobium and barium. These superconductor are applicable for strong field superconducting magnet. Due to the low critical magnetic field, type 1 superconductor have limited technical application due to the high critical magnetic field. Type 2 superconductor have wider technical application. Example, boron, doped diamond and silicon. Some superconductor called type 1 superconductor can be made to exhibit a complete Mrs.S.ARULJOTHI effect by eliminating various chemical impurities and physically imperfection, and by the choosing proper geometrical shape and size. Other superconductors called type 2 superconductor exhibit only a partial Mrs.S.ARULJOTHI effect at intermediate magnetic field strength, no matter what the geometrical shape or size. Type 2 superconductors show a decreasing expulsion of magnetic field as its strength increase until they abruptly cease being. Superconductors is relatively strong magnetic field. This graph is also example of type 1 and type 2 superconductors. Examples of superconductor: number 1, aluminium, niobium tin, niobium titanium, rare earth barium. Bismuth, strontium, calcium, copper oxide is a type of cuprate superconductor having the generalized chemical formula being the most commonly studied compound. This is classified as a class of high temperature superconductor that do not contain any rare earth elements. It was first discovered in 1988 by Hiroshi Maria and his colleagues at the National Research Institute of Metals in Japan. Though at that time they were unable to determine the precious composition and structure. The potential application of bismuth, strontium, calcium, copper oxide superconductor include superconducting chips for quantum sensor, quantum computers and quids. Another one, superconductivity materials. We know that there are lot of materials available where some of them will superconduct, excluding mercury. The original superconductor are metals, semiconductor, etc. Every different material will turn into a superconductor at a little device temperature. The main problem by using most of these materials is that they will superconduct in few degree of complete zero. The power plants that obtain electricity to your home in downward then superconducting wires will noisily. So it will conserve enormous amount of exertional energy. However, if you want to cool huge parts, all the transmission wires within the plant to complete zero, probably you will waste more energy. Then difference between semiconductor and a superconductor. Semiconductor, the resistivity of the semiconductor is finite. In this, electron repulsion leads to finite resistivity. Superconductors don't show perfect diamagnetism. The energy gap superconductor is the order of few electron volt. Flux quantization is superconductor in 2 electron units. Another one, superconductor. The resistivity of the superconductor is zero electrical resistivity. In this, electron attraction leads to the loss of resistivity. Superconductors show perfect diamagnetism. The energy gap of superconductor is the order of 10 power minus 4 electron volt. The unit of superconductor is E. Another one, properties of superconductor. The superconductor materials show some amazing properties which are essential for current technology. The research on these properties is still going to recognize and utilize these properties in various fields. Infinite conductivity or zero electric resistance, Mrs.S.ARULJOTHI effect, transition temperature or critical temperature, Josephson current, critical current, persistence currents. First one, infinity conductivity or zero electric resistance. In the superconducting condition, the superconducting material illustrates the zero electric resistance when the material is cooled under its transition temperature. Then its resistance will be reduced to zero suddenly. For instance, mercury shows zero resistance under 4 Kelvin. Mrs.S.ARULJOTHI effect. When a superconductor is cooled under the critical temperature, then it doesn't permit the magnetic field to go through in it. This occurs in superconductor is known as Mrs.S.ARULJOTHI effect. Transition temperature. This temperature is also known as critical temperature. When the critical temperature of the superconducting material is changing the conducting state from normal to superconducting state. Another one, Josephson effect. If the two superconductors are divided with the help of thin film in the insulating material, then it forms a junctions of low resistance to found electrons will copper pair. It can tunnel from one surface of the junction to the other surface. So the current because of the flow of copper pair is known as Josephson current. Critical current. When the current supplied through the conductor under the condition of superconducting, the magnetic field can be developed. If the current flow increases beyond a certain rate, then the magnetic field can be enhanced, which is equivalent to the critical value of the conductor at which is returned to its usual condition. The flow of current value is known as the critical current. Next one, persistence currents. If a superconductor ring is arranged in a magnetic field above its critical temperature, at the present cool the superconductor ring under its critical temperature. If we eliminate this field, then the flow of current can be induced within the ring because of its self-inductance. From Lenz's law, the induced current opposes the change within flux that flow through the ring. When the ring is placed in a superconducting condition, then the flow of current will be induced to continue. The flow of current is named as persistent current. This current generates a magnetic flux to make the flux flowing through the constant ring. Next one, the electrical properties of superconductor. In the electrical properties arranging due to unique and specified physical properties play an important role as what is superconductor without any such interesting electrical properties. One of such properties is the zero electrical DC resistance present in the material. This is common property of all superconductor irrespective of physical properties of the material such as the heat capacity, critical temperature, etc. Although different materials have different critical temperatures, once the temperature drops down from the critical temperature, the resistance falls to absolute zero. Thus, it indicates that superconductivity in a superconductor is the thermal property, and hence after having reached a superconducting state, the phenomenon is independent of the physical properties of the material. All the superconducting materials behave in the same manner. Another one, in magnetic field. This is the example of magnetic field diagram. When material changes from non-superconducting state to superconducting state, there are significant change in the physical properties of the material, which are the characteristic of phase transition. When the temperature drops below the thermal superconductor, there is an ejection of the magnetic field. However, when there is an external magnetic field applied to the superconductor and which is more than the critical magnetic field, the superconductor leaves the superconducting state and starts to behave as the normal conductor. This change in the phase of superconducting materials occurs due to change in Gibbs free energy. In the superconducting phase, the Gibbs free energy of the conductor is lower than the normal non-superconducting phase of free energy. When a finite amount of free energy is applied extremely to the superconductor through the external magnetic field, the free energy increases quadratic alloy in the superconductor and reaches the normal free energy value. Thus, a phase transition takes place in the conductor from the superconducting phase to the non-superconducting phase. Another one, thermal properties of superconductor. The thermal properties of superconductor are vastly different from normal electric conductor. Some of the electrons in normal conductors are not bound to individual atoms but are free to move through the materials. That is, their motion constitutes an electric current. However, these so-called conduction electrons are scattered by impurities, dislocations, grain boundaries, and lattice vibrations. But in superconductor, there is an ordering among the conduction electrons that prevents this scattering. Because of this, electric current can flow with no resistance at all. The ordering of electrons is called copper pairing. It includes the momentum of the electrons rather than their position. The energy per electrons that is associated with this ordering is quite small. One attribute that superconductivity remain unexplained for so long is minute energy changes that happen during the transition between normal and superconducting state. Hundreds of materials are said to become superconducting at low temperature. 27 metals are superconductors in their usual crystallographic forms at low temperature as well as pressure. In addition to this, around 11 chemical elements including metals, semimetals or semiconductors turn into superconductor at low temperatures and high pressures. Examples of these materials are uranium, zirconium and selenium. Also, most of the superconductors are alloys or compounds. A compound can be superconducting even if its constitution chemical elements are not. Examples include silver fluoride and a compound of carbon and potassium. Certain semiconducting compounds become superconducting when they are properly doped with impurities. These compounds are called fluorides. They have superconducting transition temperature higher than that of classic temperature. Thus, these properties of the superconductor make it possible to be used for a variety of purposes. Advantages: a superconductor is the substance that conducts electricity without any resistance, no loss of energy. The main advantage of device made from superconductor are low power dissipation, high speed operation and high sensitivity, transforming the electricity grid, improving wide band telecommunication, aiding medical diagnosis. First one, transforming the electricity grid. The electric power grid is among the greatest engineering achievements of the 20th century. Demand, however, is about to overwhelm in it. For example, the North American blackout of 2003, which lasted about 4 days, affected over 50 million persons and caused about 6 billion in economic loss. Superconductor technology provides lossless wires and cables and improve the reliability and efficiency of the power grid. Plans are underway to replace by 2030 the present power grid with a superconducting power grid. A superconducting power system occupies less real estate and is buried in the ground, quite different from present-day grid lines. Next one, improving wideband telecommunication. Wideband telecommunication technology, which operates best at gigahertz frequency, is very useful for improving the efficiency and the reliability of cell phones. Such frequencies are very difficult to achieve with semiconductor-based circuitry. However, they have been easily achieved by high-press superconductor-based receiver using a technology called Rapid Single Flux Quantum or RSFQ, Integrated Circuit Receiver. It operates with the aid of 4 Kelvin Craycoller. This technology is showing up in many cell phone receiver transmitter towers, aiding medical diagnosis. One of the first large-scale application of superconductivity is in medical diagnosis, magnetic resonance imaging or MRI. Uses powerful superconducting magnets to produce large and uniform magnetic field inside the patient's body. MRI scanners, which contain liquid helium refrigeration system, pick up how these magnetic fields are reflected by organs in the body. The machine eventually produced an image. MRI machines are superior to X-ray technology in producing a diagnosis. Paul Litterper and Sir Peter Mansfield were awarded the 2003 Nobel Prize in Physiology or Medicine for their discoveries concerning magnetic resonance imaging. Under the significance of MRI and by implication superconductor to medicine. Disadvantages of superconductor, although useful in device range of applications, superconducting materials are active only when they are kept at low temperature. Every superconducting material has a temperature below which it becomes active. This temperature is called transition temperature. Keeping them below the transition temperature involves a lot of expensive cryogenic technology. Hence, superconductors still do not show up in most everyday electronics. Scientists are researching ways that can make such superconductor operates at room temperature. High cost of cooling with liquid helium. The another one, application of superconductor. Superconductors are noted for their zero DC electrical resistance, low power loss because of less dissipation of energy, high speed operation because of zero resistance and continuous flowing electrical current and high sensitivity. The usual and well-known superconductor examples are mercury superconductor, niobium, tin superconductor, lanthanum, barium, copper oxide superconductor, and yttrium, barium, copper oxide superconductor. Application of superconductor include medical, MRI or NMR devices, magnetic energy storage system, motors, generator, transformer, computer parts, and a sensitive device for the measurement of magnetic field, electrical current, etc. Future possible application involves high performance smart grids, electric power transmission, transformers, electric motors, magnetic levitation device, superconducting magnetic refrigerator, etc. Superconducting materials have come to use experimentally to speed up connection in computer chips. Superconducting coils are used to electromagnets in MRI machines. There are used in generator, particle oscillator, transportation, electric motors, computing, medical, power transmission, etc. Superconductors mainly used for creating powerful electromagnets in MRI scanners. So these are used to divide. They can also be used to separate magnetic and non-magnetic materials. This conductor is used to transmit power and long distances. Used in memory or storage elements. Superconducting magnet. Labs application, generator, storage energy, magnetic levitation, trains. This is also the application of superconductor. Another one is the Mrs.S.ARULJOTHI effect. Mrs.S.ARULJOTHI effect, the expulsion of the magnetic field from the interior of material that in the process of becoming a superconductor, that is losing its resistance to the flow of electrical current when cooled below a certain temperature called the transition temperature, usually close to absolute zero. The Mrs.S.ARULJOTHI effect is properly of all superconductor was discovered by German physicists W. Mrs.S.ARULJOTHI and Archenfield in 1933. As a superconductor in a magnetic field is cooled to the temperature at which it abruptly loses electrical resistance. All are part of the magnetic field within material is expelled. Relatively weak magnetic field are entirely repulsed from the interior of all superconductor except for the surface layer about 1/1,000,000 of an inch thick. The external magnetic field may be made too strong, however, that it prevents a transition to the superconducting state and the Mrs.S.ARULJOTHI effect does not occur. Another one, Josephson effect. Josephson effect flow of electric current between two pieces of superconducting material separated by a thin layer of insulating material. Superconductors are materials that lose all electrical resistance when cooled below a certain temperature near absolute zero. The subsequent experimental verification of the Josephson effect lends support to BCS theory. The Josephson current flows only if no battery is connected across two superconductors. If a battery is inserted, the current oscillation very rapidly so that no net current flows. The presence of magnetic field near the superconductor influences the Josephson effect, allowing it to be used to measure very weak magnetic field. According to the BCS theory, superconductivity is a result of correlated motion of electrons in the superconducting solid. Part of this correlation is the formation of pair of electrons called copper pair. According to Josephson, under certain circumstances, these copper pairs move from one superconductor to other across the thin insulating layer. Such motion of pairs of electron constitutes the Josephson current, and the process by which the pair of cross the insulating layer is called Josephson tunneling. The Josephson effect is central to the operation of superconducting quantum interface device, that means QUID, which is very sensitive detector of magnetic field. It is used to measure tiny variation in the magnetic field of Earth and also of the human body. Another one, superconducting magnet. In the superconductivity, there is no energy dissipation because the resistance is zero. Without energy loss, many superconductor materials can carry 1,000 times larger current densities in comparison with the conversion conductor copper, for example, that make it possible to use superconductor for building lightweight, high intensity, compact magnets in many applications. Nowadays, the magnetic field can be produced using superconductor magnet. Using superconducting wires instead of a transformer's copper coil reduce the electrical energy losses by 80 to 90% and total weight by 2 to 3 fold. Magnetic field in MRI line the spin in high magnetic field hydrogen atoms are forced to accept the energy from the magnetic field. They then release this energy at a frequency. If conventional material in coils, high current needed, however the losses and heat are high. Therefore, it replaced by superconductor and cooled by helium or nitrogen. This is the MRI scan picture. Another one, lab applications. Particles can be accelerated, deflected and focused by the field of superconducting magnet. In bubble chambers, high magnetic field are used to deflect particles, forcing them to flow a curved path. The curvature and the direction of the track determine the momentum and the charge of this particle. Also, magnetic field in nuclear magnetic resonance NMR is produced using superconductor. Then generator. Generator that use superconductivity wires are using with far more efficient than conventional generator. The efficiency of superconductor electric generator is above 99% and size is reduced by half. Another one, storage energy. Superconducting materials are used now to storage energy. A distributed superconducting magnet energy storage system, that is DSMES. In Wisconsin, 3 MW for each unit. Superconductor based transformer are used also. Another one, magnetic levitation train. Superconductors perform extremely well in the magnetic levitation. A train can float on superconducting magnetic, virtually eliminating friction between the train and its tracks. Commercial use of maglev technology occurred in 1990 with the nationally funded project in Japan. This is the magnetic levitation train picture. Another one, high temperature superconductor. High temperature superconductor are defined as material that behave as superconductor at temperatures above 77 Kelvin, the boiling point of liquid nitrogen, minus 321.1 Farad. High temperature is only in respect to previously known superconductor, which functions at even colder temperature close to absolute zero. Absolute terms, these high temperature are still far below ambition and therefore require cooling. The first high temperature superconductor was discovered in 1986 by IBM researchers Bednorz and Miller, who were awarded the Nobel Prize in Physics in 1987 for the important breakthrough in the discovery of superconductivity in ceramic materials. Most high superconductor materials are type 2 superconductor. The major advantage of high temperature superconductor is that they can cooled by using liquid nitrogen opposed to the previously known superconductor, which require expensive and hard to handle coolants, primarily liquid helium. The second advantage of high temperature materials is they retain the superconductivity in higher magnetic field than previous materials. This is an important when constructing superconducting magnets, a primary application of high temperature materials. The majority of high temperature superconductor or ceramic materials are opposed to the previously known metallic materials. Ceramic superconductors are suitable for some practical uses today, still have many manufacturing issues. For example, most ceramics are brittle, which makes the fabrication of wires from them very problematic. The main classes of high temperature superconductor is copper oxide combined with other metals, especially the rare earth barium copper oxide, such as yttrium barium copper oxide. The second class of high temperature in the practical classification is the ion-based compound. Magnesium dichloride is sometimes included in high temperature superconductor. It is relatively simple to manufacture, but its superconductor only below 43 degree Kelvin, which makes it unsuitable for liquid nitrogen cooling approximately 30 degree Kelvin below nitrogen triple point temperature. Some extremely high pressure hybrid compounds are usually categorized as high temperature superconductor. In fact, Many articles on high temperature superconductors can be found on this research on high pressure gases which are not suitable for practical application. The current record holder in carbonaceous sulfur oxide beating the previous record held by lantern decay hydride by nearly 30 °K. Examples of high temperature materials. Cuprate superconductor include lanthanum, yttrium, barium copper oxide, which is famous as the first material to achieve superconductivity above the boiling point of liquid nitrogen. Last one, a SPID. SPID is also superconducting quantum interference device. Is an electronic system which uses a superconducting ring in which one or two small insulating layers have been inserted. SPID based on the Josephson effect in sandwich of superconductor, insulator, superconductor and on the flux quantization in the ring makes it ultra sensitive to any magnetic field. It can measure magnetic field up to 5×10⁻⁻18. Then today's session we are going to learn superconductor, types of superconductor, properties and then application and also high temperature SPID. Thank you.